All right, so hey, good afternoon, everyone. I wanted to share my journey into Rust, which I know some of you have been watching or participating in, and motivated a little bit, explain a little bit of history, the problem that I was seeking to solve, kind of how I came to Rust to take a swing at it, and kind of what the journey was there and what my conclusions are so far. So, and some of the things that I particularly liked about it. The TLDR is definitely that I like Rust a lot. It's been really honestly terrific. I'm actually kind of hard pressed to talk about the most disappointing things with it. There we go. Thank you, Josh. I've been hard pressed to really come up with my most disappointing thing, although maybe I can brainstorm a little bit and come up with something good. All right, so to give folks a history, and I've already given a couple presentations on this, so I don't want to belabor what state maps are. This all dates back to us trying to understand the performance of systems that are furiously doing work, but not doing the work that we want them to do, and trying to visualize what they're doing in the small. We came up with this this kind of way of visualizing state. And maybe I could come up with show you a couple of examples of that. Actually, we'll go to this. An old Postgres state map. So this is what a state map looks like. This one's actually a little hard to read because it's sorted by entity, by process ID. But this is showing you Postgres activity over time. This span covers 60 seconds, so it's not very much time. And each one of these lines is an entity. In this case, it's a process. And if I click on this, I can get some information about what process that is. This is the check pointer. We can see in this particular example, we were spending, the check pointer was off CPU due to TX wait. In terms of what actually generates this, we've got, this consumes JSON that has been generated by some other vector. So in our case, it's generally dtrace. So we look at one of these scripts over here. This is the repo. These are a bunch of example scripts that generate the kind of output that we can consume, state maps consume. So that one in particular is this script here. So this is a dtrace script that's a little unfortunate because it is generating JSON, which gets a little bit ugly from D. But this is generating a JSON payload or a JSON output file that is then consumed, can be consumed by this program called Statemaps, which generates the SVIG. The SVIG is, I think I'm the only person on the planet that pronounces them SVIGs. I know everyone pronounces, if you pronounce them SVGs, and you are now thinking like, wow, I've been pronouncing them incorrectly my whole life, that's not correct. I am pronouncing them incorrectly, and I'm unable to change myself. So don't isolate yourself the way I have isolated myself and keep pronouncing them SVGs, but to me, they're SVIGs. I also say pings, but I think more people say pings than PNG. Anyway. And GIF, not GIFs, but whatever. These things, it generates a SVIG. The great thing about SVIGs is you basically get the full DOM, which is the document object model, and state maps themselves generate programs in the form of these SVIGs. So actually, if I go over, and let me actually go just look at that. So we've got the, this is the actual SVIG that we're looking at over here. And you can see that much of it is this actual program here. So we've got an entire program that is able to process its input file. And then if I scroll further down, we'll see that this is like a bunch of rect badness. These are the actual recs that correspond to the state map. And then it knows how to, if I zoom in, for example, it knows how to change the mapping effectively to zoom in on this image really efficiently. And then I can regenerate state maps for different time offsets and so on. So those are state maps kind of in a whirlwind overview. If I were to show you, let's view the output file that was consuming. So this is the raw file that generated the state map that that I just showed you. So this is it's concatenated JSON, and the descript that you saw generates this. And the problem that I was seeking to solve is, in addition to actually just making this thing, originally this was done as one might do. This was done purely in Node. This was done 100% in JavaScript. And my opinion on that has been like, well, I'll go solve performance when it's actually a problem. But performance is such a problem with this thing that I almost can't demonstrate it for you. Let's see if I still have a window. Hopefully I still have a window up where I did this, because the performance is so deeply pathological that it actually takes almost too long to demo. So I think I've got it over here. Yeah, so this is a file that is actually not that large. This is an output file that is only 229 megabytes of output, which represents 60 seconds. This file has what? That is 3.9 million records. Doesn't feel that long. The original JavaScript version of this takes 1 minute and 26 seconds plus to run on this. And I wanted to run it on much larger files. I wanted to run it on, this is only 60 seconds of data. I wanted to run it on much larger input, like 800 megabytes, a gigabyte, and so on. And the Node version just did not cooperate at all. Just did not. It would get into GC hell and die. And there are ways that I could make that more efficient, but I actually felt that the right thing to do was to actually implement this in a hybrid of Node and C. So I did this thing called Statemaps.c, and pull that up. So this is the JavaScript state map, and over here I'm going to pull up the this is the .c file, and this is the thing that we do and only we do, where we are. And this thing's actually setting my tab stop. I think to it's got my Vim file got confused, and it is set my. There we go. That's what that should look like. This is what we do and only we do, which is developing these kind of weird hybrids where there ends up being, if you're wondering how this works, there has to be a glue file that sits between the C and the JavaScript and is basically getting us across this kind of blood-brain barrier where we're dealing with a bunch of gnarly, gross C++ to pull, and you can see me using the preprocessor there to make it look a little more tenable, but we're basically pulling data out of C and getting it into JavaScript where it can be processed. And this worked a lot better. So we saw the, I was just timing the statemap.js on this file, took 1 minute and 26 seconds. And if we go to run just the statemap code, which this is the JavaScript C hybrid, and if I run that, let's get time on that. C.fig. We'll see that this is a lot better, and this is actually one of the things that's important. It should be a lot better. Be a lot better. You should be better. Well, there we go. Okay. That's a lot better. So 11 minutes, I felt like 11 minutes, 12 seconds versus a minute, 26 seconds. That's a huge speed up. It's, obviously factor of nearly 10, and allowed for us to iterate much more quickly and was much better, and use much less DRAM. And I could run it on multi-gig input files and so on. So that was great, and that was a win. But there were a variety of reasons that it felt not really sustainable. One is it was taking a long time to add new features. So one particular feature that we wanted to do based on an idea that Jan had, although he may not have realized that he had it at the time, when we were looking at a CPU state map, he thought, wow, it'd be really nice if we could understand what was on CPU at that particular time. And develop something called tags that allow us to, and I don't want to demonstrate that now, but allow us to actually break down in this other dimension. But it was really painful to implement in C. It just took a long time to get right. And not for, I think that, there are kind of like the traditional perceptions of C are that it takes a long time to get right because of memory safety issues or what have you. It's like, oh, no one knows how to like malloc and free. Malloc and free is not really the problem. It's like malloc and free is actually pretty straightforward. I know how to write a program without rampant data corruption. That is like, that's pretty easy. The problem with C is severalfold. One, you are at such a low level from a memory perspective that it's very hard to actually compose systems out of libraries. So the libraries for C tend to be very frameworky. So if you look at, for example, a library to parse JSON, like I want to parse JSON in C. Surely there got to be some good libraries for parsing JSON in C. And the answer is like, not really. The ones that are very complete are super frameworky, where it takes control and kind of calls into you, and not very fast, honestly, which is like, what the hell am I doing this for if it's not very fast? In my case, it's very important that we mmap this file. We mmap the file and then parse the JSON out of the memory map. So that was just not really compatible with a bunch of JSON parsers, which wanted to be able to read the file for themselves. What I ended up using was something that was great that I love called Jasmine. Jasmine, and I can show you all of Jasmine. Jasmine is super minimal, done by some kind of like nutty Russian dude. And let's see here, that's the license, that's Jasmine.c. So this is all of this JSON parser. And it is what? It's 314 lines of code. Oh my God, it's so minimal. It is very, very, very minimal, very, very bare bones. It was super fast and did what I wanted it to do, but it just took a lot of hand manipulation to get it to work. And again, not of the kind of data corrupting ilk, not of the like, I don't know how to free memory ilk, but more of just the actual mechanics of using something that was so low level. So that was kind of a pain in the butt. And then when it was a big pain in the butt is that now I want to actually manipulate this thing and I want to use modern constructs to do it. I want to throw things into hash maps and kind of, flip them around and iterate over them and so on, where I don't care about the performance as much, where I care about the performance a great deal in this hot loop where we're processing records. But once we're done, I don't care about performance as much because we've reduced, and the reason for that, just to give a little bit of explanation, is we've reduced the input set a lot. So we've got an input set that's basically arbitrarily unbounded rather. And as we're processing that, we are processing these state transitions that form rectangles from a visual sense of states. As we process those rectangles, we are going to coalesce rectangles into coalesce states. So if I look at, to show this visually, so if I look at, for example, this state right here, this state is actually a coalescence of God only knows how many states. It'd be interesting to rerun the state map and learn how many states are in this one transition, which is 51% off CPU due to semop, but God only knows what it is doing the rest of the time. And actually, let's actually, just to show that, I'll use our traditional state map tool to show you, let's zoom in on that a little bit. So we're gonna begin at this offset. And we're gonna do a 1 second duration. And we're gonna do it for that input file. We'll call that zoom.sig. That will take probably another 11 seconds or so. And what this is going to do is generate another file that will zoom in on just this period of time. And we'll see that there are many more states there. So it's, oh, come on. Where did I put that? Excuse me. So this is the same actual data, even though you can see it looks really different. This is the same period of time, but this is what happens when you don't coalesce away all those states. So you can see that now a bunch of things are actually leaping out at us that we might not have seen earlier. And you can see that there's actually a lot more going on, but when we process this thing, the way we can prevent this fig from being 200 megabytes or more is that we are constantly coalescing these rectangles away. We are creating much less data that represents many more states. Anyway, so that is kind of the overview of the state map problem. The problems with C were that it was hard to add new features. It's hard to add new features because anytime I wanted to add something new, I was having to go back across the node blood-brain barrier and having to deal with this really just grotty C++. And so all of that was a real pain. But I still have this performance constraint. So what I'd like to do is have this all in one language that can be super fast, but also very flexible. And that kind of naturally brought up Rust. Rust is a really interesting language. This is not going to be necessarily an introduction to Rust. I want to give you just a somewhat of a whirlwind of some of the things that I've run into and show you some of the Rust that I've written and some of the things that I've kind of discovered along the way. So if we, let's see here, hopefully I'll never have to see that glue file again. It was great to delete that last night. So let's actually go to the my main file here. You can see this is Rust over here in this right window. Actually, both these windows are Rust. And it looks a lot like it's very C-ish, which to me, the aesthetics have got kind of a very C aesthetics to them, which I certainly appreciate. One thing just to get out of the way is white space. I did not want to be a prisoner to my own opinions on white space. So I wanted to just adopt whatever the prevailing white space was in Rust. And the prevailing white space is 4 space tabs and not using hard tabs. So soft tabs with 4 space tabs, so fine. My C and JavaScript will remain hard tabs. I'm still a hard tab purist, at least with respect to C, but I'll definitely adopt the prevailing style here, which to me ends up being very readable. And I would actually not want to do hard tabs for Rust because you end up creating scopes a lot, and you end up a little bit deeper than you are in C with less cognitive load. I mean, because I've always believed, part of the reason I believed in 80 columns and hard tabs for C, or 8 space tabs for C, I guess, is because I have always believed that if you are 6 or 7 scopes in C, it is definitely time to refactor. In Rust, that ends up being less the case because you end up creating scopes. So it's a little more reasonable to be further over. I still believe in 80 columns, and I find that my Rust has ended up being pretty readable to my eye. So let's see, a couple of things here, and I'm not going to explain everything, but just some things that are interesting. And let's actually go to where we open a file. Should we go to I'm going to pass all of this test code, which is its own thing that I'd like to talk about. So we'll get to that in a second. And sorry, let's see here. Okay, so this is the actual core of the state map ingestion loop. So a couple of things that actually merit attention. One is this use of the word unsafe. This is the only unsafe you're going to find anywhere in here, but Rust does allow you to break out of the constraints that it places on you and become unsafe should you so desire. We are being unsafe here because we are actually going to mmap the file. So we are going to create a giant piece of memory that Rust doesn't know about. Or Rust is that it can't do it safely. But so that's the unsafe there. We don't need to talk more about that. But one thing you'll notice is that we are, so this is all of this code that is statting the file, it's opening the file, it's mmapping the file, and then it's turning into UTF-8 and cranking. Something I love about Rust that is not prominently featured is this code is all robust with respect to error checking, even though it really doesn't look like it. If you look like it at first blush, you're like, wait a minute, it's doing an open of the file, but what happens if that fails? Well, if that fails, so when you open a file, it will return this file object that you can, a file structure that you can manipulate, but it actually doesn't return a file structure. What it actually returns to you is a result. And a result is one of these algebraic types. You can see the results up here. The open paren, close paren is the, that's a Rust notion of void. So instead of returning void, you return what is actually an empty tuple. I'll talk about tuples in a second. But we are returning a result. And what this says is this can either be of a void type or it can be an error type. Ignore the box for a moment. The way you're going to differentiate, so what you get back is one of these two things. It's either an error or it's this underlying payload. And you can't just use it if it's as if you need to actually determine which one of these things it is before you actually use it. And let's see if I can find an example of, actually go to my, go to the statemap.rs and see if I can find an example of where we are, let's see, there we go. So here's an example of where we are, from string radix, which is saying that I'm going to specify the radix, I specify that as 16. I'm going to pull, I'm pulling an RGB value from a color. That also does not return, you can't just use that result. You have to first determine if it's okay. That is to say, if it is not the error type, but rather the okay type, then I can actually unwrap it and actually get to its underlying type. This is all, I mean, very clearly documented. This is actually one of the, since I have invited the internet to code review my Rust and point out a better way to do it, this line is actually one of the ones that there is a less verbose way to actually do exactly what this is doing, which is probably a better way of doing it. This is not necessarily a great way of doing it, but it's very explicit, and that it's showing you what it's doing. And you'll see, one of the things you'll see a lot is these unwraps in Rust. And an unwrap says, hey, I know that this is an actual value and not an error, so give me the value of whatever this is, whether it's an option or a result. Option types and result types are the ones that you see a lot of. If you call unwrap and it's not actually a thing, if it's a none for an option or if it's an error for a result, your program will die. You will panic. So you should never do this in a way that you aren't certain that it's not. This is your equivalent of dereferencing a null pointer in Rust, even though it's not at all a null pointer. It is a fatal operation for the program, and the program immediately dies. It's very interesting to kind of watch the discussion as it evolved over time about whether a Rust program should die when it encounters this programmatic error. We, of course, believe strongly that this is a programmatic error and should result in program death. And it's very interesting to see that the Rust community broadly shares that view. So to get back to what's going on over here, what we actually need to do is we need to see if the file open has returned something that is actually okay, and then actually get the underlying file. So I'm just actually going to show you what this code would look like, because what we actually want to do is want to match file open of file name. And match is a pattern matching operator, very, very important in Rust. You can use it again and again and again. And what I'm saying is I want to change my behavior. It's a switch statement based on what type this is. And if it's okay, and that's a file, then I am going to want to say, that we can now process the file or assign to a variable or whatever. If it's an error, I probably want to then actually return the error or process. I either want to propagate it up or I want to process it. And you would see this is what you actually want to go do. Well, what they realize is like, hey, we're doing this a lot. We are doing this like all the time. We're doing this anytime we call something. We are matching to see what it is. And if it's something that is legit, we want to look at it. And if it's an error, we want to propagate it. Now, one point is I love the fact that this is the way they deal with errors. That you don't have, you look at like all the other how do languages deal with this? So languages like C++ and Java will toss an exception. And I don't like exceptions because they allow you to write code that is totally oblivious of the underlying failure mode. Like your code has actually got no idea, and you're just gonna shit your pants and let someone else try to clean it up at some other stack frame above you. I mean, it allows you to write oblivious code that I think is a problem. So I don't like exceptions. I have never liked exceptions. I don't like them in JavaScript. To me, exceptions are the equivalent of like a sig long jump or a long jump in C, and we don't use long jump in C for a lot of reasons. So don't like exceptions. So how does C deal with this? Well, C deals with this by returning, you're going to have whatever the fuck C does. He's going to return to you a return value, and you are going to determine if that's an error condition or not. The way we have dealt with that is generally 0 means success, and -1 means failure. Sometimes 0 means failure and 1 means success. Sometimes 0 means success and any negative value means failure. Sometimes any value greater than or equal to 0 means success and only -1 means failure. Sometimes any value greater than or equal to 0 means success, and any negative value denotes the error condition that you've actually encountered. That's very common in Linux, for example. So there's no one answer, and I mean, surprise, surprise, it's just it leads to error-prone code. It leads to code that is not doing the right thing. We tend to be very rigorous about our convention. We tend to operate on handles of things. So when you use one of our libraries, and if you're in a library that's intended as we would write it, and hopefully as you would write it, and as God would write it, it is, I'm going to have a mumble create operation that is going to return to me a handle to this thing. I'm then going to have mumble verb. This thing is going to return this noun to me. I'm then going to noun verb, noun verb, noun verb, noun verb, noun verb, noun underscore verb, noun underscore verb, as I call the functions to manipulate this thing. And then I'm going to noun underbar destroy it, or noun underbar free it, or somehow I'm going to noun underbar verb it to indicate I am done with this thing. And when these things fail, they will return -1, and that handle will have more information about that error, and I can call into that to get, and which works well for us, but there's nothing in the language that enforces that. There's nothing in our own code that enforces that. You could do the wrong thing. You could act the wrong way. There are lots of ways you could handle it correctly. Rust really forces you to deal with this. It says, look, or how does Go do it? Go says, I'm going to return 2 things to you. This will be, and these won't both be true, because you've done more Go, can correct me if I'm wrong, but can Go return both an error and a result at the same concurrently?
Okay. If it's doing it by returning 2 different values, yeah.
Okay, so but it's got this effectively this other channel for returning an error to you that you can ignore. I mean, I think it's somewhat hilarious and sad to me that Go will not allow you to have an import which you are not using, which seems to me to be a very a total misdemeanor infraction. I'm not using that import because I've commented out that code for right now because that's not working because I got this other fucking problem I'm dealing with. And it's like, wow, you need to delete that import. It's like, really? You can't just import that code and not use it? That is a stop the presses, I can't proceed. But not using the return value from a function goes yeah, that's cool. It's that's not cool at all. That's not, so you really can't do that. You can't say, well, I'm only going to treat the success half of this. It's you're going to have to deal with the fact that this is one of these or one of these, and your code is going to have to conditionally execute on whether it's a this or that, whether it's okay or whether it's not okay, whether it's some value or whether it's no value. I would also say that that's a nice one. Results. Options you use a lot. Options. So results are generally where you're going to have operational errors or operational issues. Options you would use if you're effectively saying this value can be a value or it can be no value at all. I mean, it's an algebraic type that includes none or some, and that is really powerful because, God, there's so much code that I have, that is, this value can be set or not, so I'm going to use a sentinel value to know, 0 denotes unset, or -1 denotes unset. Or if all values are valid values for this thing, I'm going to have some other value that says, this thing has this thing, by the way. Or I've got a bit field that says whether this value is valid, and it's just error-prone and problematic. Rust deals with that really, really cleanly. So one thing you'll see a lot, actually, just to hop up over here you'll see a lot is all of these options in here. These are things where it's I don't have to have one of these. I can have it. And that allows me to have code that's really explicit about saying, hey, if this isn't set, then I know it's a none. Otherwise, it's a sum, and I can match on it. And if I match on it and it's a sum, I want you to do this. And if it's a none, I want you to do something else. And I don't have to restrain or constrain the values it can take. So that's very valuable. Okay, so what is this question mark operator? This question mark, what they notice is we're doing this again and again and again. We're generating a bunch of boilerplate. On the one hand, I think that you have to be careful with terseness. You don't want to make things overly terse. On the other hand, I do feel like when I look at Go, oh my God, I'm seeing the same code over and over and over and over and over again. And I know those of you who've written a lot of Go are like, I never want to write this, there's particular code that you are just writing again and again and again and again and again, and that's error prone. That's error prone. It means there's a lot you need to modify if you're refactoring the source base and so on. It affects readability. So you don't want to be overly loquacious. So what Rust did, which I think is really beautiful, is they have this propagation operator, which is this question mark. And the propagation operator is saying, hey, look, you're calling something that returns a result. And if you yourself return a result and you call this thing with this propagation operator, with this question mark, what it's saying is, hey, I'm just going to deal with all that boilerplate for you. If this thing returns okay, I'm going to unwrap it for you, and I'm going to put it over here. I'm going to put it in the variable you're assigning to. If it doesn't return okay, I'm just going to handle propagating that back up to your column. So you're just going to kick out. I really, really, really like this because it allows you to have this code that is totally correct, that is not error prone, that is dealing with that is propagating errors totally properly, and yet still reads very concisely. And if I were to delete one of these question marks, we would not compile. And it would not compile because I would now be taking a result and trying to use it as something that's not a result. So, and actually, let me just do that. Let me just watch it compile right now. So I'm going to delete that question mark, and in over here, Rust map, state map, so you call it Rust map. I'm going to cargo build this, and this should fail. And it fails because it fails as soon as I try to use this. Hey, I was expecting you to use a file, and I found a result instead. So what's going on there? And what's going on there is oh crap, when I was integrating this or whatever, I forgot the question mark. It's really easy to see what's going on. One thing about the compiler, I find that the compiler generates incredibly useful error messages. I think that because they've been, Rust has been so burned by the fights that people have with the compiler, for good reason, and we'll get into those fights in a second, that when the compiler goes way out of its way. I mean, this, I love the fact that it's it underlines things for you. And okay, that may be a modern thing that exists in all languages, but that's really nice. It's saying hey, it's not just this line, which may have 50 things on it. It's it's that right there. And here's what I was expecting, and here's what I found, and I just found it to be really, really good. One thing that is funny, though, is if in a macro you delete a close paren, you can get the compiler to shit its mind on you, and it will just generate thousands of errors that you didn't have before. It can be very, very confusing. But in general, I find that the compiler generates really good error messages. So this was my, and maybe now is a good time to talk about kind of how I got into Rust. In terms of I wanted to learn Rust, what did I do? I knew the learning curve was steep, so I think I told a bunch of this, but I got the O'Reilly book on programming with Rust, systems language with Rust. What's the O'Reilly book on Rust? Take that up. I've actually got it in the programming Rust. So this is the one, I believe. Yes. The fast, safe systems development. I thought this book was great. I think it is great. I would definitely recommend this. The Rust programming language is also a very good book. That is the one that also just came out. This was just published in December. But this is a good narrative book, and I did something with this book that I have not done for a long ass time, which is I sat down and typed. They've got a fully worked example, kind of the first chapter to introduce you to this stuff, and I just typed that thing in. And it was really valuable to actually just type it in, get some things mistyped, watch the compiler complain, clean that up, figure out what I'd done wrong, and begin to get a feel for what was happening without just, I think that with other programming languages, once you learn a couple, the concepts aren't new. So you just go kind of like, you pick up a new programming language by kind of Stack Overflowing your way into existence. That is the wrong thing to do with Rust. I don't think the learning curve for Rust is that steep, but it is a learning curve. It's not just like banging on keyboard curve. And if you Stack Overflow yourself, you're gonna hurt yourself. You really want to start from first principles, from a worked example, and then I think it's not that bad. I think Rust, in many ways, like the fear of the learning curve is very healthy because it forces you to actually sit down and learn it, which has been great for me anyway. It's been fun to do that. I haven't done that for a long time. Let's see. So I having done a fully worked example, I was beginning to appreciate some of this things like the error handling work. I don't feel like the error handling gets talked about that much. I mean, maybe it does in the right circles, but people get so caught up in the memory model that they don't talk about some of this other stuff that I think is amazing. So love that. Another thing that I love is the macros are terrific. So anything that ends in a bang here is a macro. One of the things in Rust is that snprintf is kind of like a first-class citizen. They don't call it snprintf, but the ability there's a format bang macro that can format a string using this open brace, close brace syntax. And it's really cool because it gives you like full, let me see if I can find a, let me show you a couple of things. One, if you just do open brace, close brace on a println, which is also turns into a format bang, that will call effectively the toString operation. It executes the toString trait on whatever you're calling. And if it doesn't have one of those, you're not going to get a runtime exception. You're going to get a compile time exception. It won't actually compile if you don't have one of those traits. So that's very useful. The other thing that is really useful is you can have if I were to turn this into a colon question mark, that says I want you to get the debug output for this structure. Debug is a trait that you can implement. You can also derive the debug trait, and if you look at the statemap code, you'll see that I'm deriving debug all over the place, which means when we print that out, we're going to get a really nice debugging output. I think I've got a, and I can show a couple examples of that, but you'll get a nice version of the structure, which is great. Very, very helpful for debugging. So the macros, I like the macros because one of the things, if you've been in any of my code, you know that all of my C command line stuff tends to have a fatal. If you're in a command that's got fatal as a verb or as a function, you're probably in my code. I write code, and actually if we go to statemap.c, actually you won't see it because it's not standalone C file, but you'll see that fatal code takes a var args, and I generally am printing out an error message along with the command name. I like to do that a lot. I love var args. I love using the C preprocessor. Rust gives me a much more stable way, a hygienic way of doing exactly that. So I've got my own, I was able to do very quickly my own little fatal macro, and my fatal macro and this is like definitely something I was pulling off of I don't think it was Stack Overflow, but what I'm actually using is the underlying macros to do this, but I'm prepending just my command name there. And the macro rules for Rust are its own world. Rust has got really powerful macros. I am definitely a total novice at them, but I am inspired because one of the things as I reflect on my own C, I use the preprocessor a lot, and there are so many ways. When you're young and you're starting out in C, the preprocessor is is a little like having unsafe sex. To those of you who are not parents, none of you if you're not married, please practice safe sex. But you will learn that when you're married, you can actually get away with these things, and you want to actually have kids. Then the whole disposition changes. This is a terrible, terrible metaphor. I should This is one of the things a part of my brain just woke up, be like, are we seriously using safe sex? But the anyway, when you get older, you'll understand. Let me move right along. I use the preprocessor a lot, and I use it safely, and it makes my C a lot cleaner. But I would love to have more of a net in place when I'm using the preprocessor, and there's no good way to get that with CPP. And there've been some things that add features to it, but you can't reliably use them. Rust takes this to a whole new level and allows you to do some really, really cool things. Like, I'm pretty sure I use the JSON macro. I don't use the JSON macro. There is, I thought I did that for, I didn't do that because I do it as a raw string. There's, for example, a JSON bang macro that allows you to declare JSON, safe JSON inline, which is really useful. I didn't use it here, but it is really useful. Also, Rust has this R syntax, the R octothorpe syntax, or R, actually, I call that a pound sign. Cody, what do you call that?
You call it a hash.
You call it a hash, and Tobin calls it a hashtag. So if you were reading that, my son, my 13-year-old would call that, oh, that's our hashtag. It's like that. Please don't do this. Maybe we should just call it, no one calls it an octothorpe, so we should just call it an octothorpe. It is an octothorpe. But that R pound sign syntax denotes a raw string literal, which is something that I definitely miss very badly at a C, and miss in JavaScript as well. The lack of here docs are, and I'm sure ES whatever has here docs now, but it didn't back in the day, and it was a real impediment. This is another. Here's another example of a macro. This bang macro is declaring a vector. And this is a good example of something I really love about Rust, where Rust is very type safe and in all the good ways, and yet is very permissive in all of the right ways. You know, I would like to think of us as like, we are principled but laid back. And I feel like that's what Rust is. Rust is principled but laid back. So Rust is going to be up in your grill at the right time, being like, no, you can't do this. I don't know what type that is. But Rust will also infer types where it can. So when you declare something, like with this let colors equals, I don't have to say what type it is. Rust will be like, I will figure out what type it is. And I find that is so gratifying to let to be in this sweet spot of not like anything goes, where nothing is actually statically typed, but also not in this overly rigid spot, which honestly C is in, where it's like, no, I need to know everything. Like, I need to know what type everything is. The other thing that I totally love about Rust are tuples. So, Cody, you were asking the other day about multiple returns.
Yeah.
So, in Rust, a tuple is a first-class type. It's denoted with parentheses, and you can have tuples of anything. So to return multiple things, you would just return a two-tuple of whatever you want,
and you can pattern match on that,
and then you can do whatever you want. And you use, so this syntax up here, the dot syntax. So Rex in this Statemaps get Rex thing is returning that is returning an array of tuples, and so this is asserting that the zeroth member of the zeroth member of the array, that the zeroth member of the tuple is that value. So that the dot syntax is the way you denote which member of the tuple. And these are super useful for, it's like you're getting some of that lack of structure that is actually, because you don't want like super rigid structure all the time. And this is a good example where it's like, I actually don't want to have to declare, this is a classic problem in C, where in C, if I wanted this construct, I would be using a structure. I'd have to use a structure definition, and I would use a preprocessor to clean it up, to make it so I could actually have this relatively clean. In Rust, I don't need to do any of that, and Rust can figure out what this is a vector of. And in this case, it's a vector of a tuple of tuples that consist of a string and then a second member, which is a three tuple. And if I were to change this and change one of these things to not match the type signature that it inferred, it would complain. And it's really nice. I find I use tuples all the time in Rust. Just for those little structs that you need where, you're calling to a function or from a function or what have you, without having to really be overly rigid about it. Let's see. So and I won't go on absolutely forever here, but there are a bunch of things I do actually want to talk about. Talk about raw string literals. Those are great. Another thing that, and actually you can see it here, that I love about Rust. And I don't know what the state of the art is in other systems, but testing is really a first-class notion in Rust, to the point that you can have test code in your Rust code. So this hashtag, God, I can't fucking believe I just did that. Do not tell Tony I did that. God damn it. Oh, God, it's all over. It is so disappointing. This thing, this #, open bracket, test, close bracket, denotes that this code is conditionally compiled when you are running Cargo in its test mode, which Cargo is the package manager for Rust. Cargo is really nice. I think, one of the things that, Cody, I know you were saying as I got into Rust, hey, I'll be interested to hear what you think about Cargo, because I think Cargo is pretty great. Cargo is great. It is really nice. It seems to have actually learned from all these package management systems that have come in front of it. It's a package management system and a build system effectively, but it gives you that great power. But the thing I would also say is that you can just use Rust C, which is the compiler, without using Cargo. So one of the things that I should have done earlier, I wish the books would make a little bit clearer, is that because you can't use Rust C on its own, it's helpful to get in the habit of writing short Rust programs to test various things about how they work, especially if you're starting out, and doing foo.rs. And foo.rs or hello world.rs is really easy to write, and it's helpful to kind of get the fingers doing that. When you run Cargo in the test mode, and I'm going to run the Cargo test right now, what it's going to do is compile things in, all the test code is going to be compiled in, and then it's going to execute the test. So this trim multi-int, for example, it knows that this is a test to run, and it ran trim multi-int. And if I wanted to, actually I want to get more information about that. So I don't want you to capture the standard output. I want to actually see all of the standard output, and let's do that for trim multi-int. This is that whole test running. And I just love the fact that the testing infrastructure is really baked in. So this, by the way, is some of this output is that print : output as a format modifier where you're seeing that debug output. It is really nice to have your test code. And I know Dave, you and I have been around if you are running the Moray test suite, I think, inherits the lineage of CA test, which comes from AK test, which comes from the Fishworks test suite, which comes from DTest, which is a stupid program, Perl script, that runs tests in a stupid and naive way, but it's very helpful to have. We haven't had to reinvent that infrastructure, however minimal. We have to reinvent it all the time. And Statemaps are a great example where it's I know how to invent test infrastructure for Statemaps. It just didn't rise to that level. With the built-in testing for Rust, it just lowers the bar so much to write it. So this code is way better tested than the code was originally because it was easier. Again, not because I don't know how to test code, but just because for this code, doesn't really rise to it. But with Rust, I find it always rises to it. It's just super easy. And then you can have a bunch of code that is only compiled. So I only compile that print code, for example, if we're running and only compile this verify code if we are actually running with testing enabled. So it's great. I really, really, really love that. Not that any of the people that are giving me pull requests on the Statemap repo are actually running any of this right now, but it does exist. It's pretty great. So and the way it knows which test to find, by the way, is you give it a test module, and then you drop the tests in here, so it knows, okay, these are the tests that are available. You can pattern match on these things. You do all sorts of these things. You can do all sorts of things. But just in general, it's really nice. It's very shrink to fit. I found that to be really, really valuable. I wish I had used that on day 0. I kind of picked that up on day 4, and I would have done that on day 0. Okay, that's testing. The other kind of a major subject, and just because it's something that one will run into, is the way Rust deals with memory. So Rust deals with memory in a really novel fashion. Rust is trying to hit a sweet spot between explicit memory management and yet still giving composability, not having to have these kind of explicit contracts between, or implicit contracts really, between everything. And the way it does this is with an idea of ownership. And so for any given datum in Rust, there is effectively an owner to that, and there can't be 2 owners. So if you, and I'm not going to go into this in a tremendous amount of depth, other than because it merits its own deep exploration. It's one of the things that you'll need to wrap your brain around pretty early. Just like with JavaScript, I always say that JavaScript chapter 1 should be closures, even though that can be a bit heavy for the kind of the blank tag demographic. That you really need to understand closures to understand JavaScript. You really need to understand the ownership model and the way borrowing works, and the way they don't use the verb lending. I think they kind of should, because you're often lending as much as you are borrowing, where you are effectively allowing a function to mutate something, and then you're taking it back after it's done. It is a very important concept. It makes a couple of things challenging. One of the things that it makes excruciating are data structures that have, implicitly or explicitly, have data that have multiple owners. And a doubly linked linked list is the canonical example of this. Because in a doubly linked list, a node has 2 owners. Namely, it's the thing that its next node is pointing back at it, and its previous node is pointing to it. Rust is not like this. Rust is, and there are ways to do doubly linked lists in Rust. They are gnarly. And I think that there's a little bit of it, you'll see this as you get in, people will try to talk you out of a doubly linked list, be like, oh, you actually don't want a doubly linked list, which I find a little bit enraging, because I think what it should say is really question whether you want a doubly linked list. Is there another structure that can do what you want it to do? In my case, I actually wanted a doubly linked list, because what I'm trying to do is I've got these rectangles. Fundamentally, what we need to do is you've got a limit on the number of rectangles that we're going to have in this fig. So if we have a new state come in, we're processing the next datum, it represents a new state transition. We need to take some of these existing rectangles, I've got all these rectangles that are going to be in this fig. I need to find 2 of them that are adjacent, and I need to coalesce them. So which rectangles do I coalesce? And how do I keep what is the data structure for actually coalescing them? And in C, this was actually, that part of it was really easy. So in C, and actually, let me go to Statemaps source, my header file. In C, this was really straightforward, because I have an entity. An entity is like a process in for the Postgres sense. And it's got, I'm keeping track of the next entity and the next entity on the hash table of entities. So, okay, a little bit of C'ism. You got to manually do that stuff yourself. And then it's got a linked list of rectangles. And the rectangles are here. And this is something we do a lot in C. This rectangle is on 3 data structures at once. So it is on, because you can view a doubly linked list as actually nodes being on 2 data structures concurrently. they're on one linked list pointing one way, and they're on another linked list pointing the other way. And in this case, I'm on 3. I'm on one linked list pointing one way, one linked list pointing the other way, and I've got these other things. And then I'm also, importantly, I'm in a tree of these things. So I've got a tree of rectangles that because I want to find the rectangle pair that I want to coalesce. I want to coalesce the rectangle pair that represents the shortest possible state transitions. I got some algorithms doing that. And I want to find that, and then I want to coalesce it. So I need to find this thing in the tree, and then I need to coalesce it. And one of the mistakes that I made for too long was trying to figure out, I would say I was overly pleased with myself, because this is just like kind of the natural way of doing it in C. But in C, this is super easy. And we developed these data structures like AVL trees that are dealing with embedded nodes that make it just crazy easy to do it reliably. It's fast. And I'm like, I need to do the same thing in Rust. Rust did not want to do this because there's multiple ownership issues. And you can get around this with things like these ref cells, and there are ways to do things that are going to have multiple owners, but they are all gnarly. And it was just I was going into a deeper and deeper and deeper rabbit hole. And I'm like, all right, I've got to stop. And what I need to do is I need to focus on, I'm trying to solve a performance problem that I don't know for certain that I have. And my goal with the Rust implementation is not to outperform the C. My belief is that the C is going to be faster, because the C is like, it's kind of speed of light in terms of what it's doing. I don't think it's going to be faster than the C. What I want to be able to do is perform within the kind of, I don't want to be as bad as the node. If the node is 6x, 7x, 8x slower and arbitrarily slower for large state map inputs, I want to be 10 to 20 to 30% slower than the C. Let me go get this goddamn thing working, then let me benchmark it and figure out how to make it, which is, I know, makes it sound so reasonable when I phrase it that way. But it took me kind of a couple of days or longer to come to that realization that I actually just need to get something working. So how can you implement a doubly linked list in Rust without actually implementing a doubly linked list? Well, I'm sure there are many, many, many ways to do it. I'm sure the internet is going to tell me many more. But the way that I did this is a little bit funky. For a given entity, it can only, a given entity and the start time of that state is unique. There's only one of those for all the input data. So an entity can't transition into 5 states at the same nanosecond offset. So we can view that entity timestamp pair as a unique ID that we can use to actually string things together. So what I do, and you can see me do it here, is the previous pointer is not a pointer, it is a timestamp of a previous rectangle. And then I actually keep a single, for each entity, I keep a hash table of timestamps to get me to rectangles via this ref cell mechanism, but for reasons that are probably not getting to at the moment. But that's my doubly linked list. My doubly linked list is a hash table. So if you want to get to the previous one, you're gonna take this value and you're gonna look it up in the hash table. You want to get to the next one, you're gonna look it up in the hash. It's like clearly gonna be slow, because we are, instead of just doing a dereference, we are having to do a hash lookup. But as I'm thinking about it, I'm like, the hash table implementation has got to be optimized for a 64-bit value. So I don't know, maybe this won't be so slow. Then, all right, so then how do you deal with the tree? And this is where you got to get, like, again, you need to, like, when Rust is telling you that it doesn't want you to do something a certain way, definitely listen to it. And like, okay, the compiler, you don't want me to do it this way. And I'm like, I keep trying to find the way to do it, and I keep creating new problems for myself around, like, you can't deal with this mutably because I moved it over here, or like, you can't have a reference to this mutably right now because it's already borrowed or whatever. Like, okay, I need to like find a different way to do this. And in this case, what I did is like, the tree of these things is totally separate from the rectangles. So I got the rectangles over here, and then in the state map has got this by weight tree, which keeps track of these things by weights. And then when I add a rectangle, it says, hey, okay, here's what I want you to add to this rectangle tree, or if you subsume two rectangles, here's how I want you to modify this tree of weights. It ended up being like a little, on the one hand, it was a little clunkier, felt a little clunkier. On the other hand, like, it was definitely not a problem to implement. Like, Rust was like, okay, fine, I am now happy, you have pleased me, this is a good way to implement it. Ownership was really, really clear. And I was just like, I'm going to be so curious to see how this thing performs. Because one thing is, with this tree, in the AVL tree, every rectangle is a node in the AVL tree. I knew from just doing some kind of very casual profiling when I think it was running, it spends all of its time rebalancing that tree. I mean, of course it does. But it's doing a lot of pointer chasing there. I think a lot of that being the cache, but this is the B tree set is actually using a B tree instead of an AVL tree or a block tree. You can make the argument that it's going to have better memory locality. I don't know. I was just going to be curious to see. Now, the one benchmarking I had done is with SERDI. SERDI, which stands for serializing, deserializing, is an amazing crate. So crates are the Rust libraries. And SERDI does this really cool thing where it basically will generate code for you for your types on the fly that is totally safe. So what this code does, this let metadata equals, so this state, I'm saying this is state map input metadata. I need to tell you to type because Serenade JSON from string needs to know the type so it knows what type to go to. So I got to give it some type information. That's what that does there. That's pulling the string out of the payload, and then this like bundle of magic will populate one of these things or give me an error. So this has got a start, that's a vector, an array in the JSON, the title is a string, host does not need to be there, entity kind does not need to be there, that's an optional string, and then states is a JavaScript object. So it will fill all of that in with the Rust structures, and it does it with alarming speed. So when I first benchmarked this, just the JSON parsing, I first did it just with cargo build, and I'm like, and I ran up like, that is not fast at all. That's a little disappointing. I'm like, well, I'm running just like the debug build. I should just run it with the minus release. That'll give me an optimized version. Maybe that will improve things. The difference between just building it and minus release is, first of all, instead of building it in 2 seconds, it took 25 seconds to compile. It's like, wow, all right, like we got a lot of work going on. And then the artifact ran 20x faster, which is like, okay, wow. That is not, you do not get that kind of kick out of C virtually ever. Like I have never seen that kind of kick going from, I mean, even from ridiculously stupid code to, I mean, you'll see that kind of a kick. I mean, every once in a blue moon. But it's not common to see that kind of a kick in C, and it has to be a super tight loop that C can really see, and it has to be compiling it a very dumb way to a very smart way. Whereas Rust, I think, has got a lot of visibility in, I mean, Rust is this kind of grand experiment that if we restrict ourselves a little bit, and like with like the borrowing model and the ownership model, we're restricting what we do. And in return, Rust now knows all sorts of things. And in particular, it can actually drink from the holy grail of total and complete memory disambiguation. It knows that I'm going to call this function, and I know that this memory that I loaded for this thing, this function cannot possibly screw with this value. So I can leave it in a register, or I don't need to reload it. And so there are lots of ways, and clearly, I mean, I'm going to be curious to like get into the details of what they're doing. So clearly doing some great optimizations, because I think performed like a bandit for the deserialization from JSON. I'm like, man, SERDI is amazing, and SERDI JSON is amazing. And so I had like, that was kind of a very early point of total satisfaction of like, wow, I've written code that is way more robust than the C I wrote, and is as fast or faster than the C, which is kind of crazy for parsing. So wow, okay. Still was pretty convinced that when I got this whole goddamn thing working, it was not going to perform. Like I was just trying to get it to perform like roughly minus 20 or 30% would be great. And now, Let me build that. I'll build the release version of that. Chunk, 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 chunk. It ran quickly because it didn't need to rebuild the whole world. It didn't need to rebuild all my dependencies. And let's go and just remind ourselves, I think we've got it. This is not that one, this one. So we will, again, run this generating the C sig, and that before took 11 seconds and change. Would expect that to take a similar time. Yep, 11.9 seconds. And let's do target, release, state map. Same thing. And let's go to rust.sfig. How long is this going to take? Again, my guess is like, I don't know, 20 seconds, 15 seconds. So that was a surprise. So for it to be, without me I've done nothing on this. I've done zero profiling. I've made absolutely zero attempt to make this thing faster. None. In fact, you can pretty reasonably argue that I have gone out of my way to make it slower. And we are 40% faster than my C, which I did spend time on. And there are a bunch of reasonable inferences from that. I should be embarrassed about my C. I am a little embarrassed, even though like that C is like pretty good C, I think. I don't think it's leaving a lot on the table there. But that was shocking. For smaller state maps, the difference is even more eye-popping because you factor out the node startup time. So the node startup time is, it's hundreds of milliseconds, but it's hundreds of milliseconds. Whereas this thing will rip through smaller state maps because it is so lean. There is no real runtime in Rust. Everything is being done at compile time. And there's nothing behind the back kind of managing things. And one of the things I love about C is I can feel the underlying assembly. With Rust, I feel like I can feel the underlying C. I feel like I can feel like what the C would look like underneath this. And it's got that same kind of intuitive feel to it. I've been amazed actually how quickly I got to the point that I was writing like 30 and 40 lines of Rust at a time without compiling. Which for a new programming language is actually like that to me, I thought that was pretty great. I mean normally I would be like taking these baby steps and compiling, but really quickly I found that I was writing it quickly because I had a good intuition for it. I had an intuition for what it meant and what it wanted. I understood, when it wanted a reference operator and when it didn't need a reference operator. And I think, one of the open questions I have about this is like, where does Rust belong in the undergraduate curriculum? And I think you'd want to do it after C. I think you really want to have, I think the more mastery you have of C, the faster Rust is going to be. I don't think Rust is this kind of track for people who don't want to understand memory. To the contrary, I think you need to understand memory to understand why it's barking at you when it's barking at you. And it's been very helpful. And so, I'm still in terms of kind of where we are, because I don't want to kind of prattle on forever here. But in terms of where I am, I got this obviously rolled out last night. The internet is code reviewing my Rust and telling me that there are other ways to do things, which is both helpful and enraging. There are, it's very kind of like mappy foldy in terms of, which is fine, it's good, very iterator happy. There are things that you can almost always do in fewer lines of Rust. I definitely question some of these things. It's like, are we making it faster or not? I think there's going to be a lot of like actually taking a stopwatch of things to see if things are making it faster or not. People love to eliminate unwraps in particular for good reason. An unwrap can induce a panic if it's not safe to do so. But there are lots of code where it is totally safe to do so, and I don't think an unwrap is very expensive. But anyway, there's a lot to be determined there. So let's see here. Just see if there are any questions over here. It doesn't look like it. but so far, like I said, it's been great. I mean, it's been so good that I struggle to come up with the biggest negative, and I don't know which software I wouldn't use Rust for. There are some things for which it is a total home run. Any CLI tool, it's Rust would be absolutely the first place I'd go. It's really fast and intuitive for that. Mike has spent more time with the FFI. I've spent no time with FFI. I mean, what have I not done? I've not done a lot of stuff. Done nothing with FFI. I understand that is historically a real strength of Rust, and people have really raved about it. It's definitely been a giant pain in the ass for us with Node, like totally unacceptable pain in the ass about how difficult it is. The fact that it's just as difficult as it was 8 years ago is very dispiriting, if not more difficult. I love that. I'm looking forward to that. I haven't done anything with that. I haven't done anything with kind of runtime debuggability. How do I make sense of a Rust core file? How do I make sense of symbols? All that stuff. That's all in kind of the TBD bucket. From its disposition, I can already say this is going to be easier than JavaScript. I mean, given what we did with JavaScript, it's going to be a hell of a lot easier for Rust. To make sense of a core file, for example. It's just it cannot be as gnarly as it was for JavaScript, just because you don't have things moving out from underneath you and so on. So far so good. I definitely think it's to the point where I would strongly encourage people to take a really serious look, because I think for me, I just don't know what would have to happen at this point for this not to be kind of the next programming language for everything. I don't know that I would go re-implement C in particular in Rust. I don't really have any desire to re-implementing ZFS in Rust, for example, that sounds like a jail sentence. That sounds like something that you would make a political prisoner do. But adding drivers in Rust doesn't seem to be, that's a maybe, only a maybe. Doing a new CLI utility in Rust is a definite. Doing, if we had to do, when Josh was doing the binder front in C, that would be a natural for Rust. Re-implementing Moray would be a natural for Rust. So it's a spectrum. It doesn't cure all ills, but it's pretty great. And I'm deep enough into it that this isn't just the honeymoon talking. For a while, it was just the honeymoon talking, and then I had a real serious fight with the compiler, and then Russ and I needed to learn to live with one another. But I'm really I'm sold. It's really very impressive. So that's what I've got. Gone on for an hour plus. Do people have specific questions that I can answer or can't answer? I mean, with all the caveat that I am still a noob at all this stuff. I'm not been doing Rust for very long. A bunch of you have done languages that have algebraic types much more than I have. So I think that a bunch of you will pick it up faster or better than I did. Yeah, concurrency and threading is a great question. Somewhat famously or infamously, Rust originally had the end-to-end scheduling model with lightweight threads, green threads, which was very dispiriting. When I first heard about Rust in 2013 and saw they had green threads, I'm like, another thing that can't actually learn from the past. Most interestingly, Rust ripped it out, and they went through a straight native model. So the threading model it's a very C model. You create threads, and those threads go do work. Because of the ownership model, it's much easier to make things scale because there's so much that's already not shared. Because when you are writing single-threaded code in Rust, you are almost lighting up the multi-threaded parts of your brain in terms of the way you write the code. In terms of you almost are viewing like a function that you're calling as another thread that you're handing something to. It has that kind of feel to it. So it's not at all a surprise that it becomes really easy to make things parallelizable because you have to do that in order to be able to write the damn thing in the first place. All that said, I haven't done any of it yet. So, but it's traditional mutex model thread, traditional synchronization primitive with a native thread model. Patrick asked about the intrusive collections. It's not so much that didn't pan out. It's more that I realized that that was just going. that was going over land instead of taking the road. It was just going, I think I probably could have gotten it to work, but it was just going to be really painful. And my thinking was, I will go back there for performance reasons. And now I'm like, well, screw that. I'm not going back there. I think it just ends up being way too complicated with RCs are the ref counted pointers. You end up with ref cells that are themselves RC'd or ARC'd, which are atomic ref count pointers. And the code looks god awful. And you begin to question life choices. So that's part of the reason I kind of went halfway down that path. I'm like, God, this feels wrong. Before I backed out, and she was like, I just need to solve this any way, by any means necessary. I need to get this thing generating SFIGs and then figure out how to make it faster. Cool. All right. Rayon. I've not checked out Rayon at all. I have to go look at that. And I think, Patrick, this is why I think where you need a doubly linked list, maybe Rust isn't a fit. I mean, it's one of the things you kind of need to rethink the approach, or look back at the way Rust does. So Vex and the implementation of vectors, the implementation of B trees, the implementation of hash tables all use unsafe primitives. So basically, these things are unsafe, so you don't have to be. You can write unsafe things yourself, but they're unsafe, so you don't have to be. And it may be that we need to start going into, and I was going down that path a little bit. That's how I got to the Rustnomicon, which is a great name, if nothing else. The opening intro is basically like, you should not be reading this. Like, this is the dark arts of Rust. Like, go put this away. Never read this. Have a happy life. Fortunately, the folks that picked up the Rustnomicon should be finished and published, because it does create, you do need to do that. Someone needs to go write unsafe Rust. Totally. Claw2 cargo, Nick 2. It's totally got an Evil Dead kind of connotations to it. That shall be finished, because someone needs to write unsafe Rust. And it will probably need to be us at some level for some things. And again, I would not endeavor to rewrite any parts of the operating system, or really rewrite any functional software. I actually got held back a little bit by the fact I was rewriting it, honestly. Like, I actually did better and was moving faster when I stopped trying to rewrite what I had and started getting in the mode of like, okay, I need to solve the problem using Rust. So to a certain degree, rewriting things in Rust is almost a recipe for more pain. You almost want to go do greenfield software in it. And I think then that will steer you away from a need for a doubly linked list. But I don't know. There's a very good tutorial on, so you absolutely insist on learning Rust with doubly linked lists. It's pretty funny. And also it walks you through. It's actually much better about saying, look, you probably don't need this, but let me walk you all the way through it, and now you know. Oh, interesting. Yeah. So Mike, it sounds like Mike has done more stuff with multi-threaded code than I have, and has actually has waded into a bunch of the SmartOS specific stuff. And the nice thing is, I think that they're, from a community perspective, they also just seem great. Honestly, much more in line with our values than other communities. Any other questions? Yeah, totally, Patrick. In terms of like TCP, it's going to be, and that's why that is not the first thing I would go do for sure. I think the things that will definitely get interesting are as you go to think like implementing Moray in Rust, and how you deal with back pressure, how you deal with those kind of queues, where you got work queues effectively. And how you properly propagate back pressure, how you deal with the kind of the operational errors that those things have. That's going to be how we deal with the fact, because one failure mode for Rust programs surely will be that they grow without bounds. And how do you debug the Rust program that has died because it's grown without bounds? Because you just malloc yourself to death, malloc yourself out of memory and system-wide. Yeah, Moray may be, I guess I mean metaphorical Moray, maybe not literal Moray. Yeah, treat that as metaphorical Moray. A key value store. One thing that was interesting is there was a key value project that we actually just took into the CNCF that is in Rust. And I talked to those folks about it, and they were really happy with that decision. Yeah, wow, stop. It's actually possible, but dangerous. One of the things that I definitely thought of, or that I want to explore, and Dave, you and I talked about this a little bit, but I don't know what the state of the art in postmortem Rust debugging is. If we were to go tackle that problem, I would probably not do it as an MDB dmod. I would do that as a Rust program that is a debugger for Rust programs, that knows how to debug postmortem and is able to take a core file and actually process it, which is something that is a good, like elf dump would be super, almost fun to write in Rust. Like that kind of thing is really, really easy. Yeah, RDB, if RDB doesn't exist. And I think they've been using GDB and LDB, which may mean some opportunity. Right, RMDB, there we go. LDB is a bit disappointing. I mean, it's great to port it to Lumos, but it is disappointing. LDB, I think the first time I used LDB, it core dumped on me, which is what GDB can do. If I want to core dump from a debugger, I'll run GDB. Other questions? All right. Well, so anyway, it's been great. I've enjoyed it. Hopefully, I'm not too much. Hopefully, I haven't been too annoying in this whole process. I probably have been. I'm sorry. That the annoyance will probably continue as I continue to do it. Yeah, I think we should get Rust. I think getting Rust on the platform would be a great next question, great next thing to go do. And get Rust as part of the build process. And I mean, it's obviously, not easy. There's challenges there, but huge thanks to Jonathan got the modern Rust available. I know it was a lot of work to get it available on the platform full stop, but getting it in the platform would be a great next step. Not the compiler, but just being able to like add a new utility to the platform that is a Rust program would be great and a great next step. And clearly that's going to be thankless, difficult work, but I think it's going to be worthwhile to go do. I don't know, maybe that's what I'll go to next. Certainly, anytime I praise Rust with that not being done, Robert is going to go suggest that I go do that. So I'm sure there'll be a pressure, either explicit or implicit, to go do that. Anything else? Yeah, good to get a pointer to Kelly's repo. Oh, another thing I did, there was this Rust cones thing that Elijah recommended that was pretty good for like a day zero kind of a thing. It wasn't really that good beyond that. I could go extend that quite a bit at this point, but it has you kind of fill in the gaps for some Rust to teach you some basic concepts. There's a lot that it could teach you that it doesn't, but the Rust cones repo is kind of cool too. I think you can find that by Googling Rust cones. All right, well, don't be bashful about hitting me up privately if you have any questions, comments, concerns, what have you. And thanks for listening.